At first, there was nothing about the disturbance that seemed capable of commanding the attention of an entire country. Far out over the Pacific, near the vast open waters around the international dateline, a loose field of thunderstorms pulsed over a warm sea. From orbit, the system looked incomplete. Broken cloud bands, irregular bursts of convection, and a circulation that had not yet found a stable center. There was no coastline nearby, no city waiting beneath it, and no reason for most people in East Asia to know that it existed. Yet this was where the story of Typhoon Dolphin began, not with a wall of wind or a dramatic landfall, but with a subtle reorganization of heat, moisture, and motion over one of the largest oceans on Earth. Tropical cyclones are born when several atmospheric ingredients come together at the same time. Warm surface water provides energy, moist air feeds rising thunderstorms. Rotation begins to organize the developing circulation, while the winds higher in the atmosphere must be gentle enough to avoid tearing the system apart. Most disturbances never complete that transformation. They flare for a few hours or a day, then fade back into the weather around them. Dolphin did not. Over the following period, its thunderstorms became more persistent, the pressure near the center gradually fell, and the wind field began to wrap more coherently around the developing low. The storm was still thousands of kilometers from China, but its unusual birthplace already mattered. Systems that form farther east in the Pacific can spend far more time over open water before approaching the Asian continent. That extra distance can become a blessing or a threat, depending on the conditions ahead. A cyclone moving across hostile water may weaken long before land is reached. A cyclone moving through a favorable corridor, however, is given time. Time to organize, time to strengthen, and time to draw continuously from the ocean beneath it. Dolphin had been born with an enormous stretch of warm Pacific ahead. The sea did not act like a single tank of fuel that the storm could empty. It was more like a moving energy source spread beneath the cyclone's path. As warm water evaporated, moisture entered the lower atmosphere. When that moist air rose and condensed into towering clouds, heat was released, helping sustain the circulation. The process repeated itself continuously, hour after hour, provided the surrounding atmosphere remained cooperative. For forecasters, this stage of a cyclone's life is often defined less by certainty than by observation. Satellites watch cloud tops cool as thunderstorms rise. Microwave instruments reveal curved rain bands hidden beneath high clouds. Weather models begin to explore possible tracks, but at long range, every projection contains uncertainty. A small difference in the steering winds over the central Pacific can eventually become a major difference in where the storm travels several days later. At first, Dolphin was still a distant problem, a feature to monitor rather than a disaster to prepare for. But it continued westward, and each day that it remained intact increased the importance of the next forecast. The western North Pacific is one of the most active tropical cyclone regions on the planet. And communities from island chains to the coast of East Asia live with the seasonal reality of storms. Yet no two cyclones are identical. Their danger depends not only on how fast the wind moves around the center, but also on how large the circulation becomes, how quickly the storm travels, how much moisture it gathers, and what kind of landscape lies ahead. A compact, rapidly moving typhoon can produce a very different disaster from a sprawling system that carries rain across an enormous region. Dolphin was beginning to develop characteristics that made its future difficult to summarize with a single number. Its path stretched across a huge distance. Its circulation had time to evolve, and the atmosphere surrounding it was connected to a broader climate pattern that scientists were already watching closely in 2026. El Niño conditions were emerging across the tropical Pacific, altering patterns of ocean temperature and atmospheric circulation on a scale far larger than any individual storm. El Niño does not create a specific typhoon by itself, and no responsible explanation can reduce a cyclone's origin to one climate signal. But the pattern can shift the regions where tropical cyclones form and can influence the environments through which they travel. In years when development occurs farther east, some storms may spend longer periods over warm ocean before approaching East Asia. For Dolphin, that geographic circumstance would become one of the defining elements of its story. The storm was not racing directly toward China from the beginning. Instead, it was undertaking a long atmospheric journey in which each stage depended on the conditions encountered next. At times, the structure tightened. At others, changes in the surrounding winds disrupted parts of the circulation. Outer bands reorganized. Thunderstorms concentrated near the center and then spread outward again. This breathing pattern is common in tropical cyclones. They are not machines operating at a fixed setting, but evolving systems responding constantly to the ocean below and the air around them. For a viewer looking only at a satellite image, the movement may appear smooth, a spiral of clouds drifting west. In reality, the cyclone's internal structure is changing by the minute. Towers of convection rise and collapse. Rain bands rotate around the core. Dry air can erode one side while fresh thunderstorms erupt on another. The storm survives only by continually rebuilding itself. Dolphin kept rebuilding. As the days passed, the distance already traveled became part of the story. The disturbance that had once existed as a remote cluster near the international dateline was now a named tropical cyclone crossing a region large enough to make ordinary geographic intuition almost useless. Thousands of kilometers of ocean separated its birthplace from the coast it might eventually threaten. That scale is difficult to imagine from the ground. A commercial jet can cross such distances in hours. A cyclone moves far more slowly, advancing while its entire circulation rotates around a center that may itself be hundreds of kilometers across. Each day of travel exposes it to new water temperatures, new currents, new layers of wind, and new steering patterns. The fact that Dolphin continued to survive did not mean that its future was guaranteed. At any point, stronger wind shear, cooler water, or dry air could have weakened the system. That possibility is why forecasters avoided treating early projections as promises. Forecast tracks were updated repeatedly as new satellite observations and model runs arrived. The key question was no longer whether Dolphin existed, but where this unusually long journey might end. And gradually, the answer began to narrow. The steering flow pointed the cyclone toward the western Pacific and eventually toward the Chinese coast. The remote disturbance was becoming a regional threat. This was the moment when the story changed scale. What had begun as a meteorological feature over empty ocean was now moving toward densely populated provinces, major ports, transportation corridors, rivers, reservoirs, and cities, where the consequences of heavy rain could multiply rapidly. China's eastern coastline has experienced many typhoons, and its warning systems, emergency agencies, and residents are familiar with the preparations that such storms require. Yet familiarity does not eliminate uncertainty. A cyclone can alter course. It can strengthen unexpectedly. It can weaken before landfall and still deliver enormous rainfall. The most important danger may emerge far from the location where the center crosses the coast. Dolphin had not yet reached that stage, but the ingredients for a much larger story were already coming together. Its birthplace had given it distance. The ocean had given it energy. The atmosphere had allowed it to remain organized. And ahead lay a continent whose geography would transform the meaning of the storm once it arrived. For now, the Pacific still separated Dolphin from China, but the gap was closing. Forecast centers were watching more carefully. Coastal authorities were beginning to consider what a direct approach might mean. The storm that had once seemed remote was no longer easy to ignore, and the most consequential part of its journey had not yet begun. By the time Dolphin entered the western Pacific, the question was no longer whether the storm deserved attention, but how much time remained before preparation had to become action. Forecast maps that had once shown a distant spiral over open water now placed the cyclone on a path toward the coast of eastern China, and with every new advisory, uncertainty narrowed. The center was still offshore, yet the consequences of its arrival were already spreading through decisions being made on land. Ports reviewed operating schedules. Fishing vessels were ordered or advised to return to safer waters. Coastal tourism areas began restricting access. Transport operators watched wind and rainfall forecasts that could force delays or cancellations. Emergency managers shifted from monitoring to readiness, because the most useful hours in a typhoon often come before the weather deteriorates. Once the strongest rain bands reach shore, roads can flood, visibility can collapse, and evacuation becomes more dangerous. Preparation must therefore take place while the sky may still appear deceptively normal. Along the Zhejiang coast, residents had reason to take the approaching system seriously. Dolphin had crossed an extraordinary distance without losing the coherence needed to remain a major tropical cyclone, and the environment ahead was no longer an empty ocean. The shoreline it was approaching was connected to one of the most densely developed regions in China, where cities, industrial zones, ports, highways, railways, reservoirs, and river basins sit close enough together that disruption in one place can quickly affect another. The threat was not limited to the exact point where the center would cross land. A typhoon's circulation extends far beyond its eye, and the outer bands can deliver damaging weather hours before landfall. That meant communities north and south of the projected track had to prepare as well. As Dolphin drew closer, satellite images showed a mature storm with a broad shield of cloud rotating around its core. The spiral structure that looked elegant from orbit represented something very different at ground level. Violent squalls, sheets of rain, rising seas, and abrupt changes in wind direction. Near the coast, water became one of the earliest concerns. Strong onshore winds can push seawater toward land, while low atmospheric pressure allows the ocean surface to rise slightly beneath the cyclone. Waves, generated over a long stretch of open sea, can arrive before the center, battering beaches, seawalls, harbors, and exposed coastal infrastructure. Even where a destructive storm surge does not become the dominant hazard, rough seas can make marine operations unsafe and complicate efforts to secure boats and equipment. Authorities, therefore, had to think about two environments at once: the ocean, where the storm was still approaching, and the land, where its rainfall would soon begin interacting with drainage systems, slopes, rivers, and reservoirs. In the final hours before landfall, the atmosphere changed rapidly. High cloud arrived first, spreading far ahead of the center. Then lower, Darker bands moved inland, separated by brief pauses that could create the illusion that the worst had passed. Wind strengthened in pulses. Rain became more persistent. Streets that had been busy earlier emptied as people moved indoors, while emergency crews positioned equipment and monitored vulnerable districts. For residents, the experience of an approaching typhoon is often less cinematic than television images suggest. Much of it is waiting, checking windows, charging phones, moving vehicles, securing loose objects, listening for official updates, and wondering whether the forecast track will shift at the last moment. Yet the routine nature of these actions is exactly what makes them important. Disaster preparation succeeds when ordinary decisions are made before extraordinary conditions arrive. Dolphin finally reached the Zhejiang coast with winds strong enough to confirm that the long ocean crossing had not robbed it of its ability to strike with force. The moment of landfall was dramatic, but it was not a single instant in which danger suddenly began. By then, outer rain bands had already affected the region. Transportation had already been disrupted, and large numbers of people had already been moved away from exposed areas. The center crossing the shoreline was simply the point at which the cyclone's relationship with the surface below changed completely. Over water, Dolphin had been supplied by heat and evaporation. Over land, that energy source weakened. Friction increased. Hills, buildings, forests, and uneven terrain disturbed the near-surface circulation. The structure that had been maintained across the Pacific began to lose symmetry. Winds around the core started to fall, and the storm entered the stage that, in public imagination, is often associated with relief. A tropical cyclone that weakens after landfall sounds like a threat coming to an end. In meteorological terms, however, the loss of wind intensity does not automatically remove the enormous quantity of water already contained within and around the system. The transition from ocean to land can change which hazard matters most. Along the coast, the first hours were dominated by the familiar signs of a typhoon: strong wind, intense rain, difficult travel, coastal exposure, and the risk of structural damage. Farther inland, another process was beginning. Rainwater was accumulating across catchments that feed streams and rivers. Soil was absorbing moisture until its capacity to take in more water diminished. Urban drainage networks were receiving runoff from rooftops, roads, parking areas, and paved districts where little water could soak into the ground. Reservoir operators began watching inflows, not simply local rainfall totals, because water falling across an entire basin can arrive later from many directions. The geography of the event was expanding even as the cyclone itself was losing strength. This distinction would become central to understanding what happened next. A weather map might show a weakening center, yet communities located far from that center could still face worsening conditions, because rainfall depends on more than the maximum wind around the eye. Moisture can be drawn into a broad circulation from surrounding seas and monsoon flows. Bands of precipitation can repeatedly move over the same region. Terrain can lift humid air and increase condensation. Nearby weather systems can slow or redirect the remnants. Once a cyclone reaches land, its identity on a forecast chart may change faster than its ability to produce dangerous water. During Dolphin's approach, much public attention naturally focused on the coast, because that was where the storm would first arrive, and where its winds were strongest. But emergency planners had to look beyond the shoreline. Eastern China is crossed by river networks that connect local rainfall to distant downstream consequences. Mountainous areas can experience flash flooding or slope failures after prolonged downpours. Cities far from the ocean can be vulnerable if intense rain overwhelms drainage in a short period. Agricultural districts can suffer when fields remain submerged. Transport corridors can be cut, even when buildings survive the wind. The cyclone, therefore, had the potential to become less visually dramatic while becoming more geographically complicated. That transformation began soon after landfall. As the circulation moved inland, the sharpest winds diminished, but the rain shield remained extensive. Radar showed broad areas of precipitation spreading across provinces beyond the immediate coastal zone. What had arrived as a typhoon was evolving into a large inland rain system, and this change demanded a different kind of attention. Wind warnings alone could no longer describe the full threat. Flood watches, river levels, soil saturation, reservoir capacity, and the timing of additional rain became increasingly important. The public could see trees bending less violently and assume the emergency was fading, yet hydrologists and local authorities were beginning to watch a slower process that had only just started. Water was moving from streets into drains, from hillsides into streams, from small tributaries into larger rivers. In some places, the most serious consequences would not appear until hours after the strongest wind had passed. This delay is one of the reasons tropical cyclone disasters can be misunderstood. Wind is immediate and visible. Flooding can be delayed, cumulative, and distributed across a much larger area. A building either withstands a gust or it does not, but a river may continue rising long after the sky above it becomes quieter. A slope may remain intact during the heaviest downpour and fail later after water has penetrated deeper into the soil. A reservoir may absorb the first surge of inflow and face greater pressure when upstream runoff arrives. Dolphin was entering precisely the second phase. The coastal confrontation was ending, but the inland emergency was taking shape. The storm had crossed the Pacific, reached China, and begun to weaken exactly as tropical meteorology would predict. What happened next would reveal why that weakening could be dangerously misleading. The first clear sign that Dolphin's inland phase would become a separate disaster was not a dramatic surge of wind, but the accumulation of water across an expanding part of China. As the circulation weakened, rain continued to fall over river basins, already absorbing hours of precipitation, and the numbers began to tell a story that wind speed alone could no longer explain. In several locations, single-day rainfall records were broken. Weather stations that had measured countless storms over many years suddenly recorded totals beyond their previous extremes, confirming that Dolphin's most damaging legacy was shifting from the coast to the interior. In Zhejiang, Hubei, Henan, and surrounding regions, the storm's remaining circulation interacted with humid air and local terrain to produce persistent bands of heavy precipitation. Some places experienced repeated bursts rather than one continuous downpour, but the effect was similar. The ground had less time to recover between waves of rain, streams remained swollen, and drainage systems faced a volume of runoff that continued to build. By this stage, officials were no longer focused primarily on the cyclone's center. They were watching watersheds. Reservoir operators compared current levels with expected inflows. Local governments monitored mountain roads, low-lying neighborhoods, river embankments, and districts where previous flooding had already weakened infrastructure. In Hubei, warnings indicated that some areas could receive roughly 250 millimeters of rain in a single day, an amount capable of overwhelming urban drainage and destabilizing steep slopes. At the same time, dozens of reservoirs rose beyond designated safety thresholds, turning water management into a race against additional rainfall arriving from upstream. Nearly 10,000 people were evacuated from areas facing the greatest danger, not because the storm's winds were increasing, but because the landscape was becoming saturated. That distinction mattered. A flooded river basin responds to accumulated water over time. Once soil becomes saturated, even moderate additional rain can generate rapid runoff. When rivers are already high, new inflows have nowhere to go. When reservoirs are near operational limits, managers must balance holding back water against the risk that retaining too much could create greater pressure later. These are not decisions that can be judged from a single radar image. They depend on what has already fallen, what is still expected, and how quickly water is moving through each catchment. Dolphin had become a hydrological event as much as a meteorological one. The storm's influence was now being measured in river stages, reservoir levels, evacuations, and road closures rather than in maximum sustained wind. In some cities, streets turned into temporary channels as drainage networks struggled to keep pace. Vehicles stalled in deep water. Underpasses became dangerous traps. In rural areas, fields disappeared beneath muddy runoff, cutting access to farms and villages. On mountain roads, authorities faced the additional threat of debris flows and landslides. The soil on a steep slope can appear stable until water penetrates deeply enough to reduce friction between layers of earth and rock. When that threshold is crossed, failure can occur suddenly, sometimes after the most intense rainfall has already passed. The emergency, therefore, stretched across both space and time. Communities that had escaped the strongest coastal weather could still face serious consequences a day later. By then, the remnants of Dolphin were spreading farther north and inland, interacting with other weather systems over China. The original tropical structure was becoming increasingly difficult to recognize, yet the moisture associated with it remained part of a much larger atmospheric pattern. This is one reason the public language used for cyclones can become misleading after landfall. A storm may be downgraded from typhoon to tropical storm, and later to tropical depression, giving the impression that each new classification represents a proportional reduction in danger. In reality, those categories describe the strength of the wind near the circulation center. They do not measure how much rain may fall hundreds of kilometers away, nor do they account for the condition of rivers and soil beneath the clouds. Dolphin demonstrated that difference vividly. Even after its central winds fell below typhoon intensity, heavy rain continued moving through central China and eventually affected areas much farther north. The geographic reach of the event became especially striking when attention turned toward Beijing and its surrounding districts. The capital lay far from the Zhejiang coast, where Dolphin had entered the country, yet the broader weather pattern carried tropical moisture northward into regions that had their own vulnerability to intense summer rain. Outer districts activated high-level flood emergency responses as strong downpours developed. In Shunyi district, hourly rainfall reached 88. 5 millimeters during the flooding, an extraordinary rate capable of inundating streets rapidly even before river flooding is considered. For residents watching local conditions, the connection to a typhoon that had already weakened far to the south might not have been obvious. Meteorologically, however, the link was part of a continuous chain. Tropical moisture had been transported inland, then redistributed through interactions with monsoon flow, terrain, and other atmospheric features. The cyclone's original center no longer had to pass directly overhead for its water vapor to contribute to dangerous rain. This broader footprint challenged a common way of thinking about tropical storms. People often imagine the threat as a circle moving along a track line, with the greatest risk concentrated near the center. In reality, the most hazardous rainfall can occur well away from that line, particularly when moisture is drawn into stationary or slow-moving bands. A forecast cone is useful for showing uncertainty in the center's path, but it does not represent the full area that may experience flooding. Dolphin's inland evolution made that limitation impossible to ignore. The storm had become less visually impressive on satellite images, while the consequences on the ground were becoming more complex. Emergency services now faced multiple types of calls at once: flooded roads, isolated communities, damaged power lines, unstable slopes, rising streams, and people needing evacuation from homes that had not been considered at immediate risk during the coastal phase. In some places, rescue teams had to operate in conditions where water depth and current speed changed quickly. A road that appeared passable in the morning could be submerged by afternoon, after runoff arrived from higher terrain. A river could rise even after local rain had eased because water from upstream was still moving toward the same channel. The public often experiences flooding as a local event, but hydrology connects communities separated by large distances. Rain falling in one county can create problems in another hours later. This delayed connection is part of what made Dolphin's inland impact difficult to summarize in a simple timeline. There was no single moment when the crisis peaked, everywhere. Different regions entered their most dangerous phase at different times. Coastal communities dealt first with wind and intense rain. Central provinces then faced swollen rivers, saturated ground, and reservoir pressure. Northern districts later confronted additional downpours as the broader weather pattern evolved. The disaster unfolded like a sequence of overlapping waves rather than one dramatic strike. That pattern also complicated recovery. Crews could begin clearing roads in one area while new flooding developed elsewhere. Evacuated residents could not always return immediately because the absence of rain did not guarantee that nearby rivers had stopped rising. Engineers needed to inspect slopes, bridges, embankments, and drainage systems before normal movement could safely resume. Agricultural losses could take days to assess, especially where standing water remained across fields. Even when the weather improved, the consequences continued to move through the landscape. By this point, Dolphin was no longer being defined by what it looked like over the ocean. Its identity had changed. It had become a test of how a modern society manages water under extreme pressure, how quickly warnings can be issued, how effectively reservoirs can be operated, how cities handle sudden runoff, how people respond to evacuation orders, and how authorities communicate danger after a cyclone has technically weakened. The records broken at weather stations were important, but the larger meaning of those records lay in the systems forced to absorb the water. Rivers, roads, neighborhoods, farms, and reservoirs all became part of the same unfolding event. And as scientists examined why the storm had remained so productive for so long, a deeper question emerged. Was Dolphin simply an unusual storm that followed an unusual path, or did its behavior reveal something important about the atmospheric conditions that can make future tropical cyclones more dangerous even after their winds decline? The answer would require looking beyond the flood maps and back into the ocean and atmosphere that had sustained Dolphin from the beginning. To understand why Dolphin remained a coherent tropical system for so long, it is necessary to move away from the flooded streets and look again at the atmosphere over the Pacific. Longevity in a tropical cyclone is never produced by a single ingredient. It emerges from a sequence of favorable conditions that must remain aligned over time. The first of those conditions was geography. Dolphin developed unusually far to the east, near the international date line, which meant that it began its life with an immense expanse of ocean between its birthplace and East Asia. That distance alone did not guarantee survival, but it created the possibility of a long journey. A cyclone that forms close to land may have only a few days over water before terrain disrupts its circulation. A cyclone that develops thousands of kilometers offshore can remain over its primary energy source much longer, provided the water is warm enough and the surrounding atmosphere does not become hostile. The ocean is central to this process because a tropical cyclone is, in effect, a heat engine operating between the warm sea surface and the colder upper atmosphere. Evaporation transfers water vapor from the ocean into the air. That vapor rises inside deep thunderstorms, condenses, and releases latent heat. The released energy helps lower pressure and sustain the rotating circulation. As long as the storm continues to move over sufficiently warm water, it can keep drawing from that source, but warm water by itself is not enough. Tropical cyclones can weaken over very warm seas if strong vertical wind shear tilts their structure, if dry air is drawn into the core, or if the storm's own winds churn colder water upward from below. Survival requires the broader environment to cooperate. Dolphin's long path therefore reflected more than an unusually distant starting point. It also reflected the fact that the storm encountered enough favorable atmospheric conditions, often enough to repeatedly reorganize whenever its structure was disturbed. This ability to recover is important. Tropical cyclones rarely maintain perfect symmetry for days at a time. Their inner thunderstorms expand and contract. Eye walls can change shape. Outer rain bands may compete with the core for moisture. Bursts of convection can appear on one side, while another side becomes temporarily weaker. What matters is whether the circulation retains enough organization to rebuild. Dolphin did so again and again. Its persistence was not a sign that it was immune to disruption, but that the surrounding environment repeatedly gave it opportunities to recover. The developing El Niño of 2026 added another layer to the explanation. El Niño is a large-scale shift in tropical Pacific Ocean temperatures and atmospheric circulation, not a localized storm-making mechanism. It alters trade winds, convection patterns, and the distribution of warm water across the equatorial Pacific. Those changes can influence where tropical cyclones are more likely to form and the kind of steering environments they encounter. In some El Niño years, cyclone formation in the western North Pacific can shift farther east than usual. A storm born in that region may then have a much longer route across warm tropical water before reaching East Asia. This does not mean that El Niño caused Dolphin in any simple sense. The storm still depended on immediate local conditions that developed at a specific place and time. But El Niño formed part of the larger background state in which those conditions existed. That distinction is essential because climate patterns operate by changing probabilities, not by dictating individual events. They can make certain environments more likely without determining exactly which storm will form, how strong it will become, or where it will go. The same caution applies when discussing climate change. After a remarkable event, there is a natural desire to ask whether global warming caused it. Science rarely answers that question with a simple yes or no. A tropical cyclone is the product of many interacting factors, and no single storm can serve as proof of a long-term trend. And what researchers can examine is whether the physical environment in which storms occur is changing in ways that affect risk. One of the clearest relationships involves atmospheric moisture. Warmer air can hold more water vapor, which means that when conditions produce heavy rain, there is potentially more moisture available to fall. Warmer ocean surfaces can also increase evaporation, supplying additional water vapor to tropical systems. These processes do not imply that every future cyclone will be stronger or wetter than every cyclone in the past. Natural variability remains enormous, but they can shift the background conditions toward heavier precipitation when storms interact with suitable atmospheric patterns. This is particularly important because rainfall damage is not controlled by wind categories. A storm can weaken rapidly after landfall and still carry a large moisture reservoir inland. In a warmer climate, scientists are increasingly interested in how tropical cyclones may transport water, how much rain they can produce over land, and whether the most intense rainfall rates are becoming more extreme. Another area of research concerns storm motion. A cyclone that moves slowly can produce much greater rainfall totals over one region than a faster storm of similar intensity because the same area remains under rain bands for longer. The relationship between climate change and cyclone translation speed is complex and continues to be studied, but the risk principle is straightforward. Duration matters. Dolphin's story illustrated that principle on a broader scale. Its long life gave it time to interact with multiple oceanic and atmospheric environments. And once inland, the remaining circulation became part of other weather systems, rather than disappearing instantly. This is why scientists increasingly look beyond a single metric such as peak wind speed when assessing tropical cyclone danger. Storm size, rainfall efficiency, forward speed, moisture content, terrain interaction, and the condition of rivers and soils can all determine the eventual disaster. Two typhoons with similar maximum winds can produce completely different outcomes if one crosses a sparsely populated coastline quickly while the other carries persistent rain through densely populated river basins. Dolphin belonged to the second kind of story. Its significance was not that it established a new universal rule for tropical cyclones, but that it exposed how incomplete the traditional image of a typhoon can be. The public often imagines the eye wall, and the dramatic moment of landfall. Those are real hazards, but they represent only one stage in the life of a storm. The atmosphere does not recognize administrative boundaries, and it does not end an event simply because the circulation receives a lower classification. Moisture can continue moving. Rivers can continue responding. Other weather systems can absorb and redistribute what remains. For forecasting agencies, that means communication must evolve with the hazard. Early warnings may focus on track and wind. Later warnings may need to emphasize rainfall totals, flood probability, slope instability, and river response. The challenge is not merely technical, it is psychological. People naturally interpret the word weakened as safer. A downgrade can sound like permission to relax, even when the dominant threat is shifting rather than disappearing. Dolphin demonstrated why meteorologists and emergency managers must communicate not only what a storm is called, but what it is capable of doing next. The scientific lesson is therefore more subtle than a headline, suggesting that one climate phenomenon created a superstorm. Dolphin's exceptional journey emerged from the interaction of location, ocean heat, atmospheric structure, large-scale Pacific conditions, and the geography it encountered after reaching land. El Niño helped shape the background. A warming climate may increase the moisture available to storms and intensify rainfall risk, but neither factor removes the need to understand the individual weather pattern in detail. The more important conclusion is that future cyclone risk cannot be judged by historical expectations alone. As oceans and the atmosphere continue to change, forecasters will need to pay close attention to storms that form farther from land, persist over long distances, and retain the capacity to deliver extreme water long after their strongest winds have faded. Dolphin became a powerful case study because it brought all of those elements together in one event. By the time scientists looked back across its full path, the question was no longer simply how the storm had survived. The more urgent question was what communities should learn from a cyclone whose most dangerous characteristics were not fully captured by the moment it reached shore. When the final bands of heavy rain began to weaken and the atmosphere gradually lost the structure that had once belonged to Dolphin, the emergency did not end at the same moment. In many places, the sky improved before the landscape did. Rivers remained high. Saturated slopes still carried the risk of failure. Drainage systems continued moving accumulated water. And communities that had spent days responding to changing warnings began the slower work of assessing damage. This is the stage of a disaster that receives less attention than landfall, but often determines how long recovery will take. Roads must be inspected before reopening. Bridges must be checked for erosion around their foundations. Reservoirs must be managed carefully as upstream inflows continue. Power and communication networks may need repair in areas where flooding has damaged equipment or cut access. Families returning to homes must determine whether structures are safe, whether water supplies have been contaminated, and whether another round of rain could create renewed danger. In agricultural districts, the consequences can remain visible long after floodwater disappears. Crops may be lost, soil may be eroded, irrigation systems may be damaged, and livestock operations can be disrupted. In cities, the cleanup can involve mud, debris, damaged vehicles, flooded basements, and public infrastructure that has been exposed to water far beyond its normal design conditions. The passage of a storm is measured in days, but recovery can be measured in weeks or months. Dolphin's aftermath, therefore, became part of a larger question about resilience. Modern forecasting is far more advanced than it was a generation ago. Satellites can observe the atmosphere continuously, numerical models can simulate multiple possible tracks, radar can map rainfall in real time, and emergency alerts can reach millions of people within seconds. Yet better prediction does not automatically eliminate disaster. Forecasting tells society what may happen. Resilience determines what happens when the forecast becomes reality. A city with effective drainage, well-maintained flood channels, strong building standards, reliable evacuation routes, and clear public communication will face the same rain differently from a city where those systems are weaker or overwhelmed. The same principle applies in rural areas. River management, slope stabilization, reservoir operation, road access, and emergency shelters can significantly alter the human consequences of an extreme weather event. Dolphin exposed the importance of preparing for hazards that evolve after a cyclone reaches land. Traditional typhoon planning often emphasizes wind, coastal surge, and the immediate impact zone. Those remain critical, but the inland phase demands equal attention. Emergency plans need to account for the possibility that the greatest flood risk may emerge far from the coastline and long after the circulation has lost its strongest winds. That requires coordination across regions because water does not remain within the administrative boundaries where it first falls. Upstream rainfall can affect downstream communities. Reservoir releases can influence rivers far away. Landslides can block transportation routes needed by neighboring districts. A successful response therefore depends on information moving as efficiently as the water itself. One of the clearest lessons from Dolphin is that warnings must describe hazards, not merely storm categories. Telling the public that a typhoon has weakened is technically accurate if the wind has decreased, but the message can be dangerously incomplete if flood risk is rising at the same time. Future communication may need to place greater emphasis on expected rainfall, duration, river response, soil saturation, and local terrain. A person living hundreds of kilometers inland may not consider a coastal typhoon relevant, yet that person may still be affected by the moisture it transports. Effective warnings must make that connection understandable before conditions become dangerous. This is not only a matter of meteorological accuracy, it is a matter of trust. People are more likely to respond to warnings when they understand why the risk applies to them. If the public repeatedly hears that a storm is weakening while experiencing worsening flooding, confidence in official messaging can suffer. Clear explanations of changing hazards can prevent that disconnect. Dolphin also highlighted the value of uncertainty. Forecasts are often criticized when they change, but changing a forecast is not evidence of failure. It is evidence that new information has been incorporated. Tropical cyclones move through a fluid atmosphere in which small changes can alter track, speed, and rainfall distribution. The farther into the future a prediction looks, the greater the range of possible outcomes. A forecast that communicates uncertainty honestly can be more useful than one that presents a single path with false precision. For emergency planners, this means preparing for a range of scenarios rather than waiting for complete confidence. For the public, it means understanding that the absence of certainty is not the absence of danger. Dolphin's long evolution provided many opportunities for forecasts to be updated, and each update helped narrow the range of possibilities. The challenge was to convert that evolving scientific picture into timely decisions on the ground. There's also a broader lesson about infrastructure. Extreme rainfall can expose weaknesses that remain invisible during ordinary weather. Drainage systems are usually designed around historical expectations of how much water is likely to fall within a given period. Reservoir rules are based on assumptions about inflow patterns. Roads, bridges, tunnels, and urban developments are built using engineering standards that reflect past climate conditions. If the frequency or intensity of extreme rainfall changes, those assumptions may need to be reconsidered. Adaptation does not require predicting the exact storm that will arrive decades from now. It requires recognizing that systems built for yesterday's extremes may face different stresses in the future. This is especially important in rapidly growing regions where new development changes how water moves across the landscape. Paved surfaces reduce infiltration and increase runoff. Construction on floodplains can place more people and property in areas that naturally collect water. Urban expansion can also create opportunities to improve resilience through better drainage, green spaces, retention basins, elevated infrastructure, and smarter zoning. The choices made between disasters may determine the scale of losses during the next one. Dolphin's significance, therefore, extends beyond the statistics attached to a single event. It became a reminder that tropical cyclone risk is not static. It changes with the atmosphere, with the ocean, with the landscape, and with the way societies build and prepare. The storm's long path captured attention because it was unusual, but the deeper lesson lies in the transitions that occurred along that path. A disturbance became a cyclone became a coastal threat became an inland flood emergency. An emergency became a scientific case study. Each transition required a different way of thinking about danger. By the end, Dolphin was no longer only a name on a weather map. It represented the limits of simple categories in a complex system. The storm showed that intensity is not the same as impact, that weakening winds do not guarantee diminishing consequences, and that the most important phase of a disaster may occur after the most dramatic images have disappeared from television screens. It also showed the value of preparation carried out before certainty is complete. Evacuations, reservoir management, transport restrictions, and flood warnings are often inconvenient when the worst outcome does not occur, but they exist because waiting for perfect information can leave too little time to act. In the years ahead, forecasting technology will continue to improve. Satellites will become more capable. Models will run at finer resolution. Artificial intelligence may help identify patterns faster. Sensors will provide more detailed observations of rainfall, rivers, soil moisture, and ocean conditions. Yet technology alone will not decide whether communities are safer. The decisive factor will be how well scientific information is connected to infrastructure, emergency planning, public understanding, and local action. Dolphin's journey ended when its remaining circulation finally dissolved into the broader atmosphere, but the questions it raised did not disappear with the clouds. How should cities prepare for rainfall beyond historical experience? How should warning systems describe storms whose dominant hazard changes over time? How should coastal and inland regions coordinate when the same weather system affects them in different ways? And how should societies adapt as the climate background itself continues to evolve? These questions do not have one simple answer, because no future storm will follow Dolphin's path exactly. That is precisely why the event matters. Its value lies not in predicting the next cyclone, but in revealing where assumptions can fail. A storm does not need to remain at peak strength to remain dangerous. A community does not need to be near the coast to be part of a typhoon disaster. And the end of a cyclone on a weather chart does not mark the end of its consequences on the ground. In the quiet that followed Dolphin, the Pacific continued moving, rivers continued draining toward the sea, and daily life gradually returned across the affected regions. But the atmosphere had delivered a warning that extended far beyond one season. The next major cyclone will have a different name, a different track, and a different structure. What matters is whether the lessons from this one remain in place when that next storm begins as nothing more than an uncertain cluster of clouds over a distant ocean.